So you will see a difference. We have seen Turing machines that accept input and Turing machines that do some computations like addition, multiplication, subtraction, etc. So today we are going to see how to complement a Turing machine. Okay, let's see how to complement a Turing machine and construct. Okay. And then we'll proceed with the fifth year, like the different types of different variants of flavors of Turing machine. The most important flavors, we'll see two flavors of Turing machines, and then the normal ones that we have seen, and then we'll start the fifth unit. Okay, so so we are going to solve a problem today that's a bit different. Okay, so this is another example. So this example is acceptor. Turing machine as acceptor. That type of example we are going to see, not a transducer. It's acceptor. So what we are going to do is we are going to design a Turing machine. That does not contain. We might have seen such problem in DFA. Okay, so that does not contain ABA as substring. Okay. So design a Turing machine that does not have ABA as substring. Okay, so this is the problem that we are designing a Turing machine for this. So even if you have some doubts on Turing machines, that is why for revising only, I'm taking another problem over here. So please pay attention. Okay, so basically for Turing machine and other types of machines like push-down automata or a DFA, the basic differences, there are two differences. Okay, let us just revise that and start with this problem. The basic two differences, one is like a DFA will read the whole input. Please understand, a DFA will read the whole input string. Even if you have reached the acceptance state, you might have seen a self loop or something like that. Okay, so it reads the whole input string till it extracts the whole input string, and then it checks if I'm in the final state, and then the input string is accepted. Okay, input string is accepted. But a Turing machine, once it enters the final state, okay, once it enters the final state, okay, and the input gets accepted. For this sort of problems, it's saying, okay, the input gets accepted. Fine. So we are going to design an algorithm in Turing machine. So it is possible for us to design a Turing machine that just when it enters the final state, the input gets accepted. And the second class is very important. Second difference is it's common for all Turing machines. So Turing machine, the transition function. So we might get set questions in either GATE or in MCQ here. So it's called as, I'm sorry, it's not partial differentiation, partial transition functions. A transition function is called as a partial transition function. So why do I call in PDA also it's partial transition function. In the DFA alone it's called as a transition function. In PDA and in Turing machine the transition function is called as a partial transition function. I think I left out this point while teaching PDA. So I just wanted to tell this. So this is common for both push down automata and for Turing machines. The transition function is called partial because even for deterministic machines, for deterministic PDA or for deterministic Turing machines, what we do is we do not write all input symbols. If you have noted, we would not have handled all input symbols for every state. Okay, all input symbols need not be handled in your transition function or in your diagram. You need not handle all input symbols for every state. You might have noted this. For DFA, for a finite automaton, we don't do this only for the non-deterministic cases. So non-deterministic cases, we have dead configurations, as in when you don't handle an input symbol for a particular state, that means it's rejection, right? So that is non-determinism. In the non-deterministic FA, finite automata, we see that. In PDA and in Turing machine, we have only partial transition function. That means even for deterministic Turing machine and PDA, we need not handle all input symbols for every state. So when a state and an input symbol combination is not being handled by a transition function or a diagram, then that means that it's a dead configuration. Okay, so that is why we call the transition function as partial transition function. So these are the two differences. So today we're going to see a class of problem that is that we have already seen in FA. So it does not contain AB as a substrate. So the logic that we are going to follow for then generally for this sort of problems is, for me, designing a Turing machine for acceptance of ABA string that has ABA is easier. Okay, design a Turing machine to accept a string that has ABA as substring. Okay, so first I'll design this Turing machine and then I'll get a complement of it, take a complement of it, inverse of it, to get a Turing machine that does not accept the string ABA. So if I go this way, this will be easier. So I just wanted to handle one example on this case also. So today we are going to design a Turing machine first that accepts the string that has ABA as substring. Okay, that's easy to construct. After that, I'll just change the finite to non-final, final to non-final, and the same non-final states to final. How can I move the non-final states to final? So these things I'll handle today. So what we'll do is first we design a Turing machine that accepts a string that has ABA as substring in it. It can be the start, it can be the end, it can be at the middle also. So it's a substring problem. So first, what we'll do is, let us start with the state Q0. Okay, Q0 sees a A, it transits. Okay, I'll finish the edge label. Q1 sees a B, it transits. Q2 sees a A, it transits to Q3. So in case I reach Q3, that means I've seen A, B, A continuously. So that is an accepting state. Okay, so we're not going to, it's an acceptance type of Turing machine. So the tape rewrite doesn't matter much. So I'm not going to rewrite anything. I'm just going to retain the same symbols. I'm just going to do a counting and pattern checking. Okay. So what I'll do is when I see a I'll replace with A and keep moving right. When I see a B, I'll see replace it with B and keep moving right. When I see a in the tape, I rewrite it with A again and keep moving right to the, keep moving the head, read right head, right of the tape. One symbol right to the tape. Okay, so this is what we have done. So let us complete it, like at least for the basic cases, let me complete it. So what we'll do is Q0 need not start with A. So in this case, if you leave it like this, if Q0 starts with B, your machine will reject it. So our machine should accept it. So Q0 can start with B also because we are just seeing a substring problem. So we have seen enough of these problems in DFA, the logic. So how many ever B's we see, keep loop in Q0, keep rewriting B as such and keep moving right. Okay. And so the Q0 is handled. In Q1, when I've reached Q1 means I have seen a, okay, I have seen A, right? I've seen the string A, okay? So in case, how many ever A's I see, I don't have any problem. Keep writing A again and keep moving right, okay? So it just has to be, A has to be followed by B, that's it, okay? Now, in case I've reached Q2, that means I've seen the substring, okay? So I've seen AB. So here only A can occur. If I see a B, then the pattern is violated. I have to go back and start checking from what? The initial A. So after I see AB, I can see only a A. In this case, if I see a B, I should go back and start checking from the starting A. Okay, so in that case, what I'll do is I'll just go back to Q0 because it starts with B. I'll rewrite it with B and I'll keep moving right because it's a substring. I can see it anywhere down the lane. I can see another pattern ABA. Okay. So this is the basic machine, Turing machine for acceptance case. Now we are going to, what we are going to do is we are going to take a complement of this. Okay. Complement of this. So for better understanding, this Q3, what I'll say is, I'll say Q3 can be a reject state, right? You know, complement Q3 should be what? It's a reject state, right? If it sees ABA, when it has reached Q reject, that means it has seen ABA continuously. So that string should not be accepted. So Q3, I change it with reject and I'm going to write it over here. Okay. I'm going to write the complement over here. So for now, I'll not decide on any states. I'll copy the diagram as such. Okay. I'll copy the diagram as such. I'll not have anything as final state. I'll have Q reject as such. I'm pretty much sure that if I reach this Q reject, the string should be rejected. That's the only thing that I know. So I cannot have it as a final state. Okay, so just I'll label all. So you can consider the same labels. It is A, move right. If you see a B, move right. If you say A, replace with A and keep moving right. So the same diagram I've copied over here. Just I'm going to change the states. Again, this is also the same. So once I see, again, I have to go back and see. Okay, this is acceptance case. Fine. Now what I'll do is, now this is definitely a rejection case. Now what all should I accept? So the language could be anything, any string that doesn't have a ABA. So all these three non-final states should be able to reach the final state. So when do I reach the final state? So all these three should be able to reach a final state. Okay, so let me have something like Q accept final state, or you can have numbers also. This is just for clarity. I'm giving it Q reject and Q accept. Okay, so all these three are acceptable conditions. They do not have the string ABA continuously. Okay, so in this cases, if I see a blank, just replace it with blank, keep moving right and enter the final state. Okay, blank, move to the right. Okay, so now this is our final Turing machine that rejects, that accepts any string that does not have a ABA, or rejects any string that has an ABA in it. Okay, so first the method is we have constructed the one that has a substring. Acceptance criteria, for the acceptance case, we have constructed a Turing machine, and then we have complemented it over here. Okay, fine. So this is how we construct Turing machine. Okay, in Turing machine, it has a infinite tape. Okay, so our input, in case, let us check with an input. So in case I have a I have an input ABA, whatever. So let us say ABB, ABA. So how does my tape look like at the starting? It looks like this, ABA, and both the sides. So programmatically, they'll have the left end as finite or closed in some cases. So we'll assume both sides is infinite and Q naught is here during the starting. Okay. So what is that? Let us consider the final machine. So when it sees the A, it moves to Q1. When it sees a B, it moves to Q2. Q2, when it sees a B again, it comes back to Q0. So why should I do this? Is in case, okay, even if I see some ABA down the lanes, I should reject it. Okay, because if I don't go back, I'll be in Q2 and it will go accept it. So definitely I should go back. So Q0, I go back. Okay, again, how many ever B it sees is going to loop, and when it sees the A, it goes. When it sees this A, it goes to Q1. Then it sees a B, goes to Q2. It sees the A, it goes to reject. So finally, it's at this state. Okay, it's at this state, and it's not a final state. So the string is rejected. Okay, fine. So Q reject. How do I do this? Is finally it will move here, right? So Q reject doesn't have a Q reject comma blank. There is no configuration for this, right? Q reject on seeing a blank, I haven't specified any branches. So it's a halting condition. So the machine stops. When the machine stops, it's not in the accepted state. So this string is not accepted by the machine, Turing machine. Okay. So this is one way of doing it.